All right, this morning we're going to go over the concept of a torque. Okay. Now a torque is primarily what we use to get something to rotate. All right. So a torque, and we use the symbol tau to represent this with a fancy looking T. There's probably other people in the world that can draw that better. It represents a force times by a distance. Now I put this little symbol right here. This means perpendicular. All right. So a perpendicular force times by a distance. All right. Now what this gives us. Well, let me draw an example. Let's say I have a pivot here. Let's say I've got something stationed to the ground and I've got a bar. Okay. I can apply a force any point along this, right? But let's say I apply a force here at the end, but I apply it this way. Okay. If I just grab right here and just pull, remember torque is all about trying to get an object to rotate. If I just pull on this, no rotation's happening. At least not to the bar itself. Okay? And so that's why we have to put this, that's why we have to specify perpendicular force. This is a parallel force. Okay, we're talking about perpendicular to my lever arm itself. Okay? And so a parallel force, meaning something that goes in the same direction as the lever arm, doesn't inspire any type of rotation. That doesn't mean this may not like slide this way, but that's not a rotation. So torques are built about rotating objects or turning them or spinning them, okay, to get that circular type motion. That's what we've been talking about recently in class. Okay, so if I want to apply this, okay, I want to rotate this, and I either need to pull up on it or pull down on it, and then it's going to rotate either this way or this way around my pivot, or it's going to have the desire to. Similar to like Newton's second law, when we had static problems, we can apply forces to an object and not have it move because things cancel each other out. We might have something similar here. Maybe this is a stationary beam sticking out like on a truss, and we hang on it or we pull on it, and it's not moving, but we know we're applying a torque to it, but that's just because the fitting on this end is resisting our torque. All right, but the torque still exists. So let's do a problem. Let's say let's do something like this. Let's say this is 2 meters. Okay, let's say this is 20 newtons, something simple. Okay, and I just want to know what the torque is, right? So you just literally plug it in. 20 newtons, okay, times by 2 meters. Gives you 40 Newton meters. Notice that my units are in Newton meters, a force times a distance. Okay, that's the difference. A lot of people are like, well, isn't a torque just a force? It's a force applied over a distance, so it's technically different. It's not the same, though very similar. All right. Now, a lot of the time, we might have problems like this. Like, what's the teeter-totter is a classic example. Okay, so we got a teeter-totter pivot here, and we've got a bar. Okay. All right. And here we've got, let's just say, it doesn't really matter. We've got someone sitting right here, and they're applying, let's say they weigh 85 kilograms. Okay, and this is 2 meters away. Okay, and then you get someone else, all right, that wants to sit in the middle. Or they're just going to sit on this side, but they weigh 110 kilograms. We just want to know what this distance is. We want to know how far away from the pivot they need to sit to cancel out the other side, cancel out the other torque. And so this brings up something we talked in class, but I'm going to review it right now. Notice, if this 110 doesn't exist, then this teeter-totter would rotate down. in a counterclockwise rotation. Okay? And if the 85 didn't exist, and the 110, doesn't matter where he's sitting, it's going to rotate in a clockwise rotation. Okay, so it's either going to go this way, or it's going to go this way. And so we need to specify which of them is going to be positive, which rotation is going to be positive, which is going to be negative. Since in class we've already talked about positive rotation being counterclockwise, okay, we're just going to say this is positive. All right, and negative for clockwise. All right. Now we do something very similar. We're just going to do some of the torques in this case, not some of the forces. We're going to do some of the torques. Okay, and I'll specify my my positive rotation, just reminding whoever it is that's looking at my work that I'm saying counterclockwise is a positive rotation. Okay, and I don't want this to move, so I'll set whatever, I'll add up all my torques that are acting on the system and set it equal to 0. All right, and so in this case I got 85 kilograms. Okay, over 2 meters. But notice something. Up here, we talked about it's a force times the distance. If I do 85 times 2, that's a mass times the distance. Okay, so we need to add gravity in here to make it a force. And then we put the 2 meters. Okay, that's positive numbers because this is going counterclockwise. And then the 110, we're going to minus that. Okay, we got gravity acting there, and then we don't know. We know this is x. Now notice something here. We'll set all this equal to 0. I got 9.8 in both. Okay, in this case, I could just divide out the 9.8. A lot of people, honestly, would just skip putting gravity in if they're given just the mass, because you can just take gravity out of everything. So you can do it this way, kind of the long way with having 9.8, or you can just eliminate the 9.8 and not worry about it. All right, so we're going to solve for x. So I got 85 kilograms, okay, times by 2 meters equals 110 kilograms times by x. I'm going to divide the 110 over to equal x. Notice the kilograms cancel, so it didn't really matter in the end anyways whether I had it or not with the 9.8 meters per second squared, because it would have canceled in the end. And so x is going to equal 85 times 2 divided by 110. So 1.55 meters. Meters is the last unit standing, so that's what goes. All right, so 1.55 meters. Pretty simple concept, not too hard. Okay, those are the majority of the problems that you're going to get in class. There will be one other type of problem that you might see. Okay, let's say I've got a wall here, okay, and I've got some beam attached here. And let's say I've got a rope attached at a 30-degree angle. Okay, at say this distance, let's say it's 2 meters again. And we can say the tension in the rope is equal to, I don't know, 60 newtons. Kind of small, but whatever. Okay, and we want to know what the torque is acting on the beam. Okay, now remember, torque is equal to perpendicular times by distance. Okay, in this case, this tension is being applied both parallel and perpendicular because it's going at an angle. So you need to draw your triangle, and I've got my x side and my y side. My x side is my perpendicular side, okay, because it's my parallel side. It's pulling it in line with the bar. But my y side is going at a right angle. It's coming up. Okay, and so what you need to do here is you need to do the 60 sine 30 to represent that perpendicular force, and then times that by your 2 meters to get your value. Okay, and then once again, if you're wondering, well, why did you choose 60 sine 30? Okay, well, you draw the triangle, and then you do sine of your angle, and then cosine of your angle. Okay, so sine of the angle is y over 60, and cosine of your angle is x over 60. And in this case, I'm looking for the one that's going at a right angle from the bar. Okay, x is lying across the bar. It's parallel to the bar, so we don't want that one. We want the one that's perpendicular to the bar. Also, others might say, well, the triangle's got this line drawn over here, so isn't that like halfway? Isn't that 1 meter away? Remember, this triangle is just a symbolic representation of what's happening at this point. So it still happens at the 2 meters. I just didn't want to draw it that small. Okay, so to solve for your y here, you're just going to times both sides by 60, and that's where the 60 sine 30 comes from. Okay, if you have any questions, let me know. Those are the kind of things you might see in class. Hopefully this isn't too confusing. If it is, please let me know. I can make another video, or we can come in and do some examples on the board. Either way, love to help you.